Today I want to finish with a simple outer bound. This outer bound is due to Thomas Kova, and it's based on our result for DMC. So from Shannon theorem, main theorem for channel coding, you know if you have a channel from X to Y, then the rate is bounded by the maximum over all px of the mutual information between X and Y. So now we can consider the two marginal channel and use the maximization over px. So for example, here we look at the mutual information between X and Y1 and the rate, because the total rate which we can transmit to the first receiver is R0 plus R1. The same is true for the second decoder. So here we have R0, that's the common message rate, plus R2, that's the dedicated rate for the second receiver. This is bounded by the maximum of the mutual information and X and Y2. When you remember, we just did the reconverse here by Fano's inequality. That was all that we used. However, rather than optimizing px for each mutual information separately, the same steps as we used before, that one can consider the same px for both bounds simultaneously, if you remember when we just use the common message. One can further add bounds based on letting the receiver cooperate. Then we get this bound here, R0 plus R1, R2 must be less or equal than the mutual information of X, Y, and Y1, Y2. So in totally, we have this rate here, and we look at this rate at the union over all px of R of px. And it turns out that the capacity region of the broadcast channel is a subset of this R bar cut rate here of Kova. And indeed, if you think a little bit, it's really based on the results on the DMC.